how did the fundamental principles and laws of physics before chemistry and biology that govern our universe originate during the Big Bang? How are these laws of nature and physics so consistent and persistent, appearing like controlled variables? Yeah, or the fundamental principles and laws of physics that govern our universe and are responsible for everything we see, these laws and principles originated during the Big Bang and the subsequent evolution of the universe, of the cosmos. Okay, so the Big Bang was when the original, what we believe to be singularity, Big Bang, primordial singularity, experienced perhaps a spontaneous expansion or whatever caused it. We don't know what caused it. Okay, so the universe began as an extremely hot, extremely dense point, approximately 13.8 billion years ago, and then it expanded. And as it expanded, it started cooling, and it underwent a series of phase transformations that set the stage for the formation of the first fundamental particles and the formation of the fundamental forces. We know of four forces: the strong nuclear force, the weak nuclear force, the electromagnetic force, and the gravitational force. So the first second of the life of the universe itself is a tremendously long epoch. The first fractions of a second, in that time, the universe was in a very, very highly dense energetic state. Okay, and then you have a period of cosmic inflation, an exponential superluminal expansion of the space. So this process of inflation, it helped homogenize the universe and set the initial conditions for the development of the physical laws that we know so well. Now, in the early stage, there was the entire universe was governed by a single law. That's what is believed. Okay, we don't know, a single unified force, super gravity or whatever you want to call it, the grand unified force. So that is what the universe was governed by initially. That is what we believe. And as the universe expanded and cooled, the symmetry broke spontaneously, and we eventually got the four fundamental forces that we observe today. So this spontaneous symmetry breaking is a key concept in understanding how the different forces and particles emerged. For example, you may have heard of the Higgs boson, the Higgs mechanism, which explains how the various particles acquire mass through interactions with the Higgs field. So that's what is believed to have happened. Now, the laws of physics that we know, they are formulated in the form of mathematical equations, and they describe the regularities and patterns of the universe. They describe the behavior of the fundamental components of the universe. We have the Einstein field equations of general relativity. We have the Schrödinger equation, wave mechanics, quantum mechanics. These are all based on various symmetries and conservation principles. So this mathematical consistency that we observe everywhere in the universe, as far as we can see, the laws of the universe are the same everywhere. And this mathematical consistency is what ensures that these laws apply apparently universally. Okay, so, and all of this is influenced by symmetry and the invariance and the transformations of various laws and so on. And we have conservation laws like the law of conservation of momentum, of energy, of mass, which ensures that everything remains consistent in the universe. And then you have the standard model of physics that provides a comprehensive framework for understanding the three forces that we kind of understand: the electromagnetic force, the weak force, the strong nuclear force. We're not quite capable of yet thus far of fitting gravitation into the standard model, but that's where you have it. Okay, and then general relativity takes care of gravitation, and all of this has been experimentally validated. The universe seems to be homogeneous and isotropic on the largest scales, which means that the physical laws should be the same everywhere in all directions, which kind of makes them appear like they are controlled variables. And we have evidence that comes in from the cosmic microwave background radiation, which tells us that the early universe had a nearly uniform temperature and density, with perhaps some regions of over densities and all that. So it's a long explanation, but that's kind of how it is. When you ask very, very fundamental questions as to how did these principles and laws of physics emerge and originate, we don't quite have the answers. For that, we need to develop what is seemingly impossible: a grand unified theory, a theory of everything, the equation that answers all your questions. But we still don't have it. So we are still kind of groping in the dark and grappling with these questions. But these are the questions that fascinate us and drive theoretical physics research forward.